Good morning and welcome back to Computer Graphics Livestream. So we're nearing the end of the term. As a matter of fact, that's the last stream for this term. And yeah, there's just a few bits and pieces to finalize, to pick up on, and to connect. So there'll be a bunch of slides today that say repetition. So they are in fact a repetition of previous streams or lectures. I just want to basically show you how things are all connected. And there are a few new things that I want to talk about today. Okay, so where were we? The last thing that I mentioned, that I talked about actually for quite a while, were scene graphs or high-level APIs. And I think I made this point clear that there's this awkward thing that high-level APIs are both, or scene graphs are both very unsuccessful when it comes to general projects, products, software pieces, and at the same time very successful when it comes to very specific tailor-made pieces of software, as they are the foundation of pretty much any application system that has anything to do with computer graphics. And one thing that I mentioned is that there's a potential when you build a big piece of software that is fairly general, either like a super general scene graph, which seems to be unsuccessful, or this at least somewhat general scene graph, for instance, for games specifically, or for virtual reality environments. If you build this piece of software, then there are a couple of opportunities to optimize the rendering process that you, of course, also have when you start to implement your software from scratch, but that might take a lot of time, a lot of effort that you don't want to spend on your small project, and you would rather use some like turnkey solution. So specifically for scene graphs, there are a couple of things that you can optimize. For instance, you can optimize the storage of assets. You could traverse the graph in some smart or not so smart way. You can spend time on the geometry itself. Hello. And of course, the entire rasterization process. That's where usually most of the time is spent. You can throw optimizations as that process. Okay, so for storage, I just put together this relatively long list here of things, and basically I could take most of that from a database lecture, like almost verbatim, right? Maybe mesh reduction here is something that you wouldn't see in a database lecture, or geometry simplification or whatever. But the basic idea is the data, be it textures or geometry or animation sequence or whatever, well, it's just data. And you have to load this potentially from a remote source over a network. You have to cache this in between. You might have to load this from local storage. It needs to be unpacked, whatever. So, and that's a very general problem. And there exist a ton of general solutions to that. Compression for data reduction, but also for performance improvement. You should not forget that today we have so much compute power that we can spend a lot of compute instead of waiting for data to be transmitted. So it, as a matter of fact, is actually faster, even from devices that are really fast, such as SSDs. It's faster to just read compressed data and decompress it instead of reading the uncompressed data, which is more data, right? So, I mean, of course, it depends on the compression scheme, but there are a ton of things that you can optimize here, and none of those, or hardly any of those, are really specific to computer graphics. So I'll skip that and just kind of look at the things that are very specific to graphics, right? And one of the things that is very specific to graphics is the ability to compress in a lossless fashion, to reduce geometry, for instance. Here's an example for a geometric reduction, but also for images, to apply a lossy compression. Did I say lossless? What I mean is lossy compression, right? To apply a lossy compression scheme. There are a ton of things where you don't want to apply lossy compression, right? If you have a text document, you don't want to lose every 10th word or so. Well, you could argue that, well, yeah, sure, we can reconstruct that, but yeah, it's not the way to go. But if it comes to graphics or music as well, right? Think about MP3, a lossy compression scheme makes a lot of sense. It reduces the data significantly better than a lossless compression scheme, hopefully, otherwise it's pretty worthless. And it's hopefully unnoticeable. And beyond unnoticeable, there's actually an advantage of velocity compression scheme if you do it in a very specific way. And you can see this here from this Beethoven bust on this slide here. So what you see on the left, there's a lot of fidelity, and then from the left to the right, more and more triangles in this triangle mesh are removed up to this point where, well, we can probably still recognize Beethoven here, but it's certainly a lot smaller in terms of its footprint in memory. But what's interesting about data reduction in a computer graphics sense is that further away objects that are relatively small on screen, not only require less detail, so it's not worth spending more memory, bandwidth, time to transfer data, compute on those, but it can actually improve the visual quality. We'll see later today why that's the case, but just as a kind of a quick pointer ahead is that if you have very small details that are smaller than they are visible on screen, you get an effect called aliasing or flickering, and that can be reduced or removed by removing small scale detail. So more on that a little bit later. But just as a side note here, it might actually not just improve performance, but also quality. Okay, so how can we simplify a mesh? I'll focus a little bit on mesh simplification here, because simplification of images, I'll cover that a little bit later, but simplification of images is generally relatively straightforward, right? If you have a 4x4 image, just drop every second one and you get a 2x2 image. Okay, so that's pretty easy. However, if you want to simplify a mesh, such as the 3 cases on the left, it's not just like, okay, let's just combine left, right, top, bottom, because the question is, what's left, right, top, bottom anyhow in a triangular mesh, right? Take the red vertex here. Which one is the top vertex and what's with the others? Okay, so if we have this type of data, it gets a little bit more complicated to do some sort of removal of parts of the structure. Okay, and there's basically 3 ways for a triangular mesh that we can remove parts of the data, and it applies to other polygonal meshes as well, but let's focus on triangles here because they're the most important type of mesh that we generally use. And one thing that we can do is, if we have our big triangle mesh, we just remove a single vertex. Okay, of course we don't just want to remove the vertex and be happy with it. We don't want to introduce holes in the structure, so we have to re-triangulate the remaining vertices or the remaining triangles. Okay? And here's an example. So for instance, we could choose one of the adjacent vertices and connect all the others to that vertex, creating new triangles in the process. So that's one thing that we could do. The other operation that we could do is, instead of thinking about a mesh as a set of vertices, we could think about it as a set of edges. And then we can just remove an edge. So basically take 2 vertices and fuse them into one. That's kind of the same thing as an edge removal. Okay, and that will sort of automatically close the hole. So no additional work that we need to spend here. Instead of thinking about the edges or the vertices, we can also process a mesh polygonal wise, and again, in case of triangles, triangle wise. So we can just take a triangle and remove it. Of course, in each case, we need to figure out which one to remove. That's another question, which I'll cover in a second. But just from a conceptual point of view, there's at least three different ways how we can remove a thing, a structure from a triangle mesh. Okay, and for the last case here, triangle, you can think about this as taking 3 vertices and fusing them onto a single point, in the process removing a triangle, and not just a triangle, but on average we end up with n-4 triangles. So we end up with 4 triangles that we remove. And if you think about this for a second, you'll easily figure out where those triangles are lost. Okay, so that's the first thing we need to decide on. If we want to start from a high resolution, high fidelity triangular mesh, we need to first figure out, okay, how do we intend to decimate this data? And from that, you can already see that for these type of structures, these meshes, there's a lot more complexity in there than, well, just those plain images that I just talked about. Okay, regardless of which one, which technique we choose, or if we choose a mixture of these methods or reduction concepts, we have to figure out which one to remove. Okay, which vertex, which triangle, or which edge should we collapse or remove. And it's quite surprising, if you have never thought about this, it's quite surprising how many different possibilities there are, and they will all potentially lead to different outcomes. Okay, so here's just a couple of examples. For instance, take the one on the top left. So if we have a triangle mesh, if it consists of a bunch of triangles, not just one or two, it's usually curved, right? If it's all flat, well, what's the point of having a ton of triangles? So what you generally assume is that if you have multiple triangles in one place, that there is some sort of a curvature in there. And then you could take, for instance, from one vertex to its adjacent vertices, you could compute the plane, the average plane in which the adjacent vertices sit. They don't necessarily sit in the plane unless it's 3, right? But the average plane, and then figure out what's the distance of that center vertex to that average plane, because when I remove that center vertex, the whole resulting mesh, the decimated mesh, will kind of flatten and will be closer to that center. The higher this distance is, the more loss, the more visual loss I'll experience by removing that vertex. Okay, that's one way of describing the costs of that vertex or the importance of that vertex. Okay. Another way would be to look at the angle. Because if you can see this here, because if I remove that vertex, then those angles will increase. Okay, so again, this thing flattens out, so the angles will increase, whereas if that vertex is further and further away, those angles shrink. Okay, so again, that's another metric of figuring out how important that particular vertex is. Okay, and there's others. I just put a couple of them here on this slide. So there's certain distances that we can look at. Okay, so how far is something away? I've covered a few of those distances just on the previous slide, like the distance in terms of angular distance or distance in terms of like actually Euclidean distance. We can also look at the curvature right away. So how curved was something before, how curved is it afterwards? However, again, a warning here, curvature, even though it sounds very intuitive, it's actually not that simple to define. Okay, I'll not cover curvature so much here. I'll probably cover it in advanced image synthesis next semester a little bit more, but just to give you an idea, since your mesh is a two-dimensional manifold, there's not just one curvature, there's multiple curvatures. There have to be at least 2 for 2 principal directions, and so on and so forth. Which one do you want to use? And so it gets a little bit more messy here. You can also look at other things such as the area before and after simplification. What I mean is the surface area. In general, when you remove a vertex, the area shrinks. So that's something that you can look at. There's also a more elaborate metric such as the quadratic error metric, which is something that has been pretty popular and sometimes is still used for relatively simple schemes. But I just want to cover the first concept here, just distance. And my idea here is really just to give you some sort of a taste how complicated things get once you try to work with meshes. So right now, I don't offer a mesh processing lecture in Duisburg-Essen. That might change in the future if I get the time to design one. But just to give you an idea how relatively simple ideas can get complicated when we think about these sets, these mesh structures. Okay, distance. Well, okay, first of all, distance for points is trivial, right? You got a point A and point B, and let's say we're in Euclidean space, then this is just like the root over the sum of the squares of the components. So that's pretty simple, right? It's A squared plus B squared and root over that. So in 2D, okay, simple as that. Now let's make things a little bit more complicated. And let's think about what's the distance from one mesh to another. Okay, not just point, but one mesh to another. And there's actually a ton of different distances that you can compute. And just want to talk about the most simple and most intuitive one here. At least I think it's the most intuitive one. And that's the so-called Hausdorff distance. Okay, and it's defined between two sets, A and B. And those are the surfaces. So A and B are the sets of points on a surface, and it's simply defined as the maximum over the distance and some other maximum over another distance, whereas each of those distances is the minimum over a distance. Okay, so now that doesn't look intuitive at all, and frankly I haven't explained what these distances are, but you'll see in a second, or in a few minutes maybe, that this is actually a relatively intuitive metric. Okay, so first of all, we need to figure out what are all those letters here about. Okay, maximum, minimum, I guess that's clear. Okay, if we've got a set of things, a set of numbers, so we're just talking about simple numbers here. Maximum, I guess, doesn't require much of an explanation, so does minimum. Okay, cool. The trouble is just what's the maximum over what's the distance over two sets? Okay, that's what we're trying to answer, right? Our definition here says the distance of a surface A and a surface B. Okay, so now what is that? And surface in our case here, the uppercase A and B, those are triangulated meshes. Okay, so those are basically sets of vertices. Okay, now. And you can't just say, okay, well, give me the distance between those two triangle meshes. That's what we're trying to solve. So we're trying to break this down to a metric that makes that we know. Okay. And what did I start with a few minutes ago? I started with by saying, okay, we can compute the distance between 2 points. Yeah, that's something that we know. Okay. So basically, what this Hausdorff distance does, it relates the distance between two sets. The two meshes, it relates that to the distance between points. Okay, and that's basically what this lowercase ab distance is. Okay, so this is simply the distance between a point A and a point B. So we know what that is, and generally, again, we're dealing with Euclidean spaces. We might have different crazy spaces from time to time, but here it's straightforward. Here, I mean, not just Hausdorff, but computer graphics mesh simplification, right? This is just really the difference between x, y, and z coordinates of the points A and B, and then squared and root over those. Okay, that's easy. Now, that's this part here, okay? That's this distance part here. Let's make myself a little bit bigger. Okay, so this is this part here. Now, what's with this part here, okay? Now, you see, this distance here that has one uppercase letter in it is defined as the minimum over a bunch of point-to-point distances. Now, notice that this one has one uppercase and lowercase. So what we're looking at, so this here is supposed to describe what's the distance of an entire mesh, right? We've got one entire mesh, okay? And we've got one point, and we want to know how far is that mesh away from that point. Okay, before we look at that definition here, let's just think about this for a moment. And my initial argument was this is actually supposed to be intuitive. Okay, so if you were to, if you forget this for a second here, and you were to compute, or you were asked to compute the distance of a point to a surface, what would you do? And I would argue that you would take that point and you would figure out to the entire surface. Right? What's the minimum distance to any place on the surface? Not just a vertex, but any place on the surface. Okay, let's just take a single triangle. Right? We've got a single triangle here. It's obviously in the plane. We've got one point here. And if I want to know, okay, what's the distance of that point to this triangle here? Then we would just compute, well, the shortest distance of all the points in the triangle. Okay? And that we would normally, I guess, consider the distance. Okay, and that's exactly what this thing here does. So it says it's the minimum distance between all points on the mesh. And notice that A is on the surface of uppercase A. So it's not just all vertices, but it's literally all the infinite amount of points that lie on the surface of the mesh. Okay, and that's the distance of a mesh to a point. Okay, and again, I would claim that this is pretty intuitive. Okay, so here we just have the other situation around a point to a mesh, and that's a mesh to a point. Now you might say, okay, of course this is symmetric. Well, nonetheless, we need both of these situations here, so I wrote them both down. Okay, so we can compute the point to mesh or mesh to point, and we'll basically do the same thing. We'll consider all the points on the surface, not just the vertices, all the points on the surface, and check for the minimum distance to that particular point. Now we take these two things, notice that they show up in this formula at the top here. We take these two things here and compute the maximum now overall points. Okay, so what does that mean? Let's first look at this first part here. Okay, so what we do here is, we want to compare two meshes, obviously, right? We want to compare the compressed or the reduced mesh to the unreduced mesh. So this is why we start with two triangle meshes. Okay, so in this here takes every point, now every vertex, right? This is not every point on the surface, that's different from here. This is every vertex of the mesh A and computes the distance to the entire surface B. Okay, and over all these points, we take the maximum. Okay, that means if we are interested in, so we've got one here, one mesh here, let's say this is our mesh, like it's a cross section, right? And we've got another one that has a little bit of a dent here, okay? And the rest is the same. So then if I'm asked, like, what's the difference between this mesh and the other one, I would of course look at that specific area where I have the maximum change, right? All the other points that are equal, I don't care about them, right? If I'm asked, like, what's the difference? I look at, like, what are the differences, right? So this is why there's a maximum. So I check the vertex that has the maximum distance to the previous surface, okay? And I do this the other way around as well. We'll see in a second that these two aren't equal necessarily, okay? And the reason is because we have this asymmetry here, surface vertices, okay? So I check, okay, go over all vertices of mesh A, check their distance to mesh B, take the maximum, and then I do the other way around. I take all the vertices of mesh B, check their distance to mesh at the surface of A. Most of these distances will be 0, but some will be non-zero. And then over these two, I take the maximum again. Okay. Now let's look at an example. I suppose that probably helps a little bit here. So I've decreased the size of the equation a little bit so that I have other space for other stuff, but nonetheless here still the same formula than before. So now we've got a cross section here through a mesh, or you could also consider this a line list. This Hausdorff distance is very, very general. Now I decide to remove this vertex here, okay? So that one here on the top. So what I get is this new mesh or line list here. Okay, now I want to compute the Hausdorff distance. Okay, so, and let's look at that. So what do I get? Well, I've got to compute these two distances here and compute the maximum over them. So we'll first look at the points on this yellow or greenish structure and compute their distance to the blue structure. And what I get is this distance here, d. Okay, well, I get a bunch of zeros as well, right? Like this point here, for instance, has 0 distance to the blue surface, but, well, I get one that is non-zero here. And that is, of course, what I would consider the distance of those two structures, right? So that's where the maximum comes from. If I compute the other way around, right? If I go over all the blue, the vertices in the blue structure and compute the distance to the yellow one, I would get 0. Okay, so you already see here that these two maxima aren't the same. Okay? Here's another example. So if that's my starting mesh and I just shift a vertex around, again, Hausdorff distance very general, doesn't only work for vertex removals, then you see that I get these two distances here. So I get one distance that is d2, that is the distance of yellow to blue, and d1 is the distance of blue to yellow. Again, those aren't necessarily equal. And I, of course, want to take the maximum over those two. Okay, so that's a metric that I could compute, for instance. Okay, so this Hausdorff distance, I could do the following. Say I want to remove a vertex from a mesh or a triangle or an edge. And I just iterate over all vertices, triangles or edges, and just remove them blindly, like one after the other, and then check which one has the smallest distance. Which one has the smallest Hausdorff distance. That one I pick, and then I delete basically all the prior information And if I want to remove another vertex, edge, or triangle, I repeat the process. Of course, I can be a little bit smarter here. I don't have to delete all the information. But nonetheless, that's one way to proceed to simplify a mesh. You can already imagine that it's pretty costly. So if I really recompute this every time, I would, of course, if I want to remove all the vertices or almost all of them, such as seen here at the top, we would end up with a quadratic approach, which is not a good idea, right? For every vertex to look at all other vertices is in the order of quadratic, right? Not a good idea if the mesh is big. So we need to be a little bit smarter than that, and yeah, retain data. And but if we do this, we can basically start from a high resolution mesh and then remove it. Say, let's just stick with the vertices for a second. Remove vertex by vertex, and what we get is a sequence of meshes from high quality to low quality. Okay, and what we can do is we can unroll that sequence. We can not just store the low quality version here, but we can store the steps that we did to get to this low quality. And the nice thing about this concept is that it allows us to do some streaming or progressive processing of a mesh. Okay, so we can start with our low resolution, and then we can just apply or undo all of those simplifications that we did up to the point where we end up with the full resolution or the desired resolution. And if we compare that one here, for instance, say I would stream this over a network, over a relatively low bandwidth, slow network. I could load this relatively quickly and then send this stream of operations to get to this full resolution point. That would lead to a, I would say, much better result than just streaming the vertices. So here at the bottom is the same situation, same full resolution Beethoven bus. I just tilted it a little bit to show the difference. And in this case here, we have the 5, 10, 50, and 100% situation, so it's here. So this is 5% of the mesh. This is then 10%, 50%, and 100%. And well, that doesn't really make much sense here, right? To display this, well, A, I can't recognize a thing, and B, if I would use that in say, a game of virtual environment, it would look pretty awkward if this would be a bust, I don't know, somewhere in a room. However, that would probably work. And then if I do this in a clever fashion, make sure that those details fade in, I would probably not even notice that I get added detail. Okay, so one nice thing about this simplification is that I can remember the process that led to the simplification and unroll it backwards and then get a streaming data structure. Okay. So we need to be very careful though with the simplification in general. So that's just a warning. Take this data set here, that's the so-called Happy Buddha data set. It's a standard data set very often used in computer graphics. And as you can see here, it's significantly simplified, down from roughly 1 million vertices down to just 3,000 or almost 4,000 vertices. And the structure is pretty well retained, right? But there are some really nasty things about this data set, and that's the topology here. So for instance, you got these holes around the arms above the head, and you got a hole here, and there's a couple of things. Since it's a depiction of a human-like structure, we want to retain, for instance, as much as possible detail in the facial area, because that's something that we use to recognize humans or human-alike structures. So bottom line is simplification, or picking where to simplify, depends on a lot of things, right? It depends on, well, distances that I described, for instance, and pick your favorite distance. There are multiple of those, but also the topology, right? Do parts of the mesh break down? If I remove parts, for instance, parts of the fingers, there's suddenly entirely areas lost, holes are lost, okay? So the topology will significantly change. And then there are other things that are even harder to handle, and those are semantic pieces of information. Again, I said faces are important, right? We want to keep, even though this is super high simplified, right? You can still get the basic idea of the face. You can still guess where the nose is, and you can see that this is a human, right? Or human like figure. Okay, so and that is something that is very hard to detect automatically. Right, it's figuring out, okay, what's the salient part of a mesh? What's an important part for for us, and I suppose we're usually dealing with humans working with the data, for us, what is an important part that needs to be kept? Okay, and all of that for a good simplification has to take into account some way or another. However, once you've done that somehow, and that's again my point, right? This is a ton of literature that you have to work on, a ton of works to get this done right, and that's something that you want to spend time implementing this into an engine. But certainly not every time you start a new project, right? You don't want to add a few million lines of code, and these things are very nasty to implement. There's a ton of corner cases. And even professional software often crashes because they run into awkward corner cases that haven't been considered properly. So it's a non-trivial task. I guess I made that point clear. However, once we've got that, I said it's good for progressive data streaming. It's good for speeding things up. We have to load lesser data, but it's also good for this idea of detail culling. So instead of rendering the full detail of, say, this dragon here when it's small, it's actually a good idea, not just from a performance point of view, but also from a quality point of view, to reduce the amount of detail. Because if that thing moves around here and we have it in full detail here, such as seen on the left, it's going to alias, it's going to flicker. Right? More on that again in a few minutes. So that's one way of getting rid of data, getting rid of details, and that's just basically what we call level of detail. So just small structures, whatever small means, again, whether that's a distance or an angle or an area or a volume, right? That's basically up to you how you intend to implement that. But anyways, getting rid of small data, it will save you some time and improve quality. Another method to get rid of data, to reduce the data, is to, well, remove things that are simply not visible. What does not visible mean? Well, it means a ton of things, actually. I'm not talking about occlusion here, so I'll actually talk about that in a minute, but not visible also means, well, it doesn't make a difference, right? So, for instance, what you see here at the top is a mesh of a BMW car that comes out of a engineering software. And as you can see, just look at the hood. I mean, it's made up of a ton of triangles. Here's quadrilaterals that can be broken down into triangles, or that are broken down into triangles. And I said before, well, if you have multiple triangles, you probably have a curved surface. Well, admittedly, that hood is curved. Here, it's slightly curved, but even if it would be totally flat, still the software would have broken that down into a ton of triangles. And the reason is that it's being used for, well, things such as a crash simulation where, well, that's not going to stay perfectly flat throughout the process of the crash. Okay, so there's often situations where the data that you get is overly complicated, despite for your particular purpose that being, well, completely worthless. Okay? So, and that presents significant opportunities for simplification, right? Notice how the geometric detail has been reduced here significantly without significant loss in fidelity. Okay, well, I guess in this case you might argue, oh, the BMW logo is gone, so that's probably a nightmare. And that again tells you that there's semantic information, not just in faces, right? So there's also important semantic information here. So if you would be a BMW executive and I would simplify this and the BMW logo is gone, you would probably go crazy. Okay, but then again, so this is probably renderable in real time and the one on the top is not. So how do we fix the BMW problem? The BMW logo problem, or it can be any other logo for that matter. Okay, and here's an idea how to fix that. Okay, so similar situation. I tried to abstract away from the BMW, but it's a similar situation. We've got a overly detailed mesh. Simplify that to a reasonable size. I mean, most of the shapes here are flat, but as you can probably see, in the lighting, there's a difference. Okay, so if you look at the lighting, the red to white distribution here, it's different here than here. okay, because we now have these big triangles, and depending on our lighting model, things will get interpolated. But we can, without reintroducing the geometric detail, we can return to the lighting situation from before, and the same is true for getting a BMW logo back on the hood of the car by using a texture. Okay, so we can use a texture, or we could use a normal map if it's just the geometry, which is really just another texture. We can use a texture to recover detail. Now you might say, okay, well, that's awkward, right? Instead of sticking with a full resolution geometry, we now reduce the geometry, saving some memory, and then we add the texture, which, well, costs additional memory. Okay, whether that's a normal map or whether it's a color map, an albedo map, which just contains color information, doesn't really matter. But you could say, oh, we could stick with the geometry right away. Well, not entirely. So first of all, generally, textures are smaller. Okay, just think about, you use a bunch of triangles just for representing a logo instead of a bunch of pixels. So a triangle is usually made up of 3 vertices. I say usually because they are shared amongst triangles, right? But nonetheless, it'll take a lot more. It takes the color information and the position information of the triangle, whereas the texture is simpler in that regard. So it's most likely smaller, and it's more flexible. What do I mean by more flexible? Again, remember my remarks from a few minutes ago where I said, well, to simplify texture is trivial, right? I mean, just take 2 by 2 pixels and then shrink them into 1, and you got your lower resolution. So it's also easier to work with these textures. Okay, so that said, when you remove detail, you might want to add some of that detail back through, if it's about lighting, normal map, or if it's about color, just color maps. What else can we do? Well, another interesting thing is just to change the order of things. For instance, for vertices, you remember probably, or probably not, from the very early beginning of this lecture, where it was still a lecture in presence and not a live stream, that I said there's multiple ways how to store triangles or to send triangles to a graphics card, right? So I said there's a GL triangle thing. I explained this with OpenGL, but it's true for any API. There's GL triangles, and then there's GL triangle strip or GL triangle fan. And the advantages of, for instance, strips and fans are that they save a lot of bandwidth. Okay, so for instance, in this case here, when we have these 4 triangles, I could submit them as 4 separate triangles. The first one made up of vertex 0, 1, and 2, and the second one of 1, 2, 3, and so on and so forth. But I can also say, okay, well, those have a specific structure. They are in a strip. And then I can send them just as 0, 1, 2, and then just 3. So I just send a single vertex, and the hardware will automatically take my last 2 vertices, 1 and 2 in this case, and use them as the other 2 vertices of a triangle. And then so on. So I send 4, and 2 and 3 are reused. So there's some small details here. So if you think about this for a moment, you'll notice that the winding order will change, right? 0, 1, 2 is clockwise, whereas 1, 2, 3 is counterclockwise, and you don't want to change the winding order. So the graphics card has to do a little bit of magic here, but more on that later, more on winding orders in advanced image synthesis. It works, so let's just say for now it works. You can submit things as a strip if they have the structure here. Or same is true for a fan. So if you have the structure that there's a bunch of triangles that are centered around a vertex, you can just send that vertex first, and then after the first 3 vertices that still make up the first triangle, just submit 1 additional vertex, and all the following triangles will be made up of the very first and the last in the one that you sent. Okay, and that reduces the amount of data significantly, because, well, except for the very first triangle, you now only need 1 vertex per triangle. And that works with index vertices as well. So even if the vertices are stored as a shared vertex list, you just need 1 index per triangle. That sounds easy. What's not so easy is to find these strips or fans. Okay, so if you have your overall mesh, just think about this for a moment, right? Think about like the BMW or the Happy Buddha or whatever mesh I've shown you today. And let's just figure out, okay, how can we find those strips? Okay, how can we find those fans? I mean, probably 1 strip or 1 fan is not going to do. So you need to have multiple of those and restart from time to time to reconstruct the entire surface. But again, that's something, how to stripify. That's the process of turning a mesh into strips. How to stripify things and how to do this in some reasonable way. That would be the contents of a different lecture, geometric modeling. Okay, so but it's a non-trivial process to do this in an optimal fashion. Whatever optimal means here, that alone is not so easy to answer. Okay, so but all of that should just give you an idea of what you can do with geometry. And that, again, is very specific, obviously, to geometry. It's not just a general database problem, right? But you can simplify it in multiple ways. Just simplify the order of things, simplify detail, maybe recover detail. So the next thing, and I just want to cover this very briefly because it's very specific to scene graphs, is spatialization, okay? So let's just show an example here. So if we're dealing with a general scene graph, we might, before we render that, want to spend some time to restructure that scene graph, to put things together that are spatially close, that reuse data, that use the same attributes, that share certain properties. Okay, so for instance, for a car with wheels, we'll probably have the same geometry for each wheel. It's just kind of rotated or shifted around. And by analyzing this graph, the traversal order can be changed, or the topology of the graph can be changed. Right? Notice that the first graph here at the top and the one in the center, despite representing the same image, have a completely different topology. So you can have a graph optimizer run on that structure and figure out, okay, where can we share resources? Right, so instead of loading the mesh for the wheels 4 times, let's just send it once to the graphics card, render it, and then maybe evict it because it's too big to fit in memory together with other data, and then render, I don't know, the body of the car or whatever. Okay, so, and that is similar to optimization of, for instance, SQL queries or so on. So these graph optimizers are a thing that you also see in databases sometimes. And the idea is here as well to reuse resources, right? To reuse query results, and here we want to reduce memory. So, and similar optimizations can be done to state changes. You want to reduce state changes because they also cost time. So, long story short, that's a thing that you can do when you implement a graph and you've got time to worry about this. Okay, now let's again briefly cover yet another topic to save data. And I said before, removing details that are not visible, or removing things that are not visible. So there's other situations other than things are just too small, detail culling. There's other methods of removing things that are unnecessary. Okay, and that's called culling. Removing parts that are invisible, that we refer to as culling. And detail culling, I already covered that one, but there's also backface culling, occlusion culling, and view frustum culling. So what are those good for? Okay, let's just look at an image here that depicts view frustum culling. Okay, so we've got our view frustum, that's the area that is covered by our camera. And in a normal scene, there's a ton of world outside. Okay, so if you look at something, it's very likely that the world behind you still exists. Okay, despite philosophers doubting that, we would just stick with the assumption that the world behind me still exists, even though I can't see or hear it. Okay, so but that means it's there, it consumes memory, it needs to be rasterized, processed, but it will not contribute to the scene. So how can we deal with that situation? And well, the first, and there's a problem here that we run into that we'll see a couple of times over and over again, and that is, well, you could say, okay, sure, let's just ignore everything that's outside the viewing frustum, right? At least that's completely outside the viewing frustum. Notice there's things that are probably partially inside. Let's process those, okay, to be on the safe side. But everything that's outside, let's ignore it. Now, what's the problem here? The idea is great, but the problem is to figure out whether, say, this sphere here is inside the frustum. I need to process it, okay? And the whole point of ignoring it was to not process it. in the first place. Okay, so we've got the chicken and egg problem here in a sense. How can we fix that? How can we like look at the sphere or that one or whatever, this cone or whatever is outside, without like having to like process it? Because then we might just render it and realize that it doesn't produce any pixels or fragments on screen. So, and what it takes is, well, some sort of an acceleration structure. And I talked about those. I'll give you a few hints in a few seconds. What were those things that you potentially missed now? But just as a pointer right now, so a spatial acceleration structure, for instance, will help. If we know that an entire subspace is not visible, we ignore the parts inside. Or some hierarchical, for instance, bounding volume a structure would be useful. Okay, instead of processing the entire sphere, let's just process some proxy, I don't know, a box around the sphere, and then use it. Okay, so in generally this kind of chicken and egg issue here that we'll encounter a couple of times is usually fixed or addressed through some sort of an acceleration mechanism. Okay. More on that again, the pointers to previous slides in a second. Before that, I still want to cover a few other culling methods because they are built on the same acceleration structure. Another thing is occlusion culling. Let's come back to that BMW for a second. And when I look at the BMW as it's visible here, right, with a pretty with a lot of opaque parts, you'll notice that, or you will not notice that a ton of things are missing, right? So there are all these parts here. The passenger, for instance, is not visible at all. Most of the motor is not visible. The front right wheel is not visible, and so on and so forth. So there's a ton of things that are just not visible, right? Some are, right? The driver, for instance, is visible, and there's part of the internals of the car, of the engine, is visible through this hole here. But a ton of things are not, and that is generally a significant amount of information that is just occluded. And there's situations where this is super significant. Take a city, for instance, right? Standard example, assume you're standing in Manhattan, right? You have a highly detailed version of the architecture of Manhattan, right? With textures and all that stuff. If I'm standing somewhere, any random given point in Manhattan, I'll only see a incredibly small part of the architecture, right? If I'm looking straight at a building, I see that building and maybe only, I don't know, 5% of that building. Even if I look along a long street, I'll just see those buildings along the street, okay? And everything else is occluded. So it doesn't make any sense to even load that data from a remote source, right? Think about something such as Google Earth or so, when you want to visualize entire cityscapes. You don't want to process all of that. But again, we run into the same issue. How do I figure out if building A is not visible, right? Like, is it covered by building B? Or, I mean, I don't generally get them in some nice order. So I get building A and building B in some random order. How do I know that building A is covered by B if I haven't even loaded B yet? Okay, so it's the same chicken and egg problem here. How do we figure out that something's not visible without rendering it? If we render it, it's trivial, right? I mean, I can just render the entire city and then look at the final result, which house, which building, which triangle contributed to the image. So once I've rendered everything, the answer is, well, the rendered image. It's literally there, but how can I reuse that? Okay, and again, there's the idea of using acceleration structures for that, and what they do is they bring order to the data. Yeah, I cover that, but again, see in a second. And another thing is making some assumptions about continuity. Okay, so for instance, I could do this really dumb approach, render whole New York. Okay, would probably take forever. But anyways, I'll just render that. I'll just have a, I don't know, 10-second delay before you see the first image. And then I would just assume that you're not a superhuman and you don't beam from point A to point B. You don't jump. Okay, so let's just pretend there's no cuts in this game. Then I can make this assumption that whatever was invisible in the current frame is probably, with a very high probability, going to be invisible in the next frame as well. Very high probability usually doesn't mean 100%. So I might make an error here. Okay, and there are all kinds of tricks around trying to fix that. For instance, if I have 1,000 buildings, right, every frame, I could just check one of those 1,000 buildings if it now became visible by just rendering it and checking if it changed the result in any way. And then after 1,000 frames, I've covered all 1,000 buildings. If I'm running at 200 hertz, that means every 5 seconds, I'm sure that my data structure is correct. And if I'm not making any rapid motion, that would be okay. Okay, you're saying we're getting into heuristic area here as well. And you've probably noticed that in games, that sometimes you got popping artifacts, right? Things pop up, so they suddenly appear where they should have been before. And that's a typical result of such an optimization technique. So it's not all just spatial acceleration, so also temporal acceleration over time, where we make use of previous results. Before I get to the acceleration structures, just a somewhat hacky thing that is still very important, and it's portal culling. So in special situations, we can assume. So for instance, let's say we've got a room-to-room scenario. You're in a cave, you're in a house, you're in a dungeon, whatever. Okay, so where we can separate certain things, where we can assign certain parts of the level of the environment of the data, we can group that. Okay, so if that's the case, and only then we can say, okay, well, there's the situation where we are on the left. So in this case, like the center of the camera is here. Okay, so that's where I am, and I'm looking towards the right. Okay, and there's a portal. And a portal is just a fancy name for a door, a connection. Okay, so here there's a door, the wall is open. Okay, and I can see that room. So that means everything in that room is potentially visible from that point. Okay, but nothing in the third room is visible because I haven't opened the door yet, or there simply doesn't exist any door from this room to that room. So there's no line of sight. So that, and then when the scene is static or it doesn't change a lot, so I mean, if I open the door, for instance, that would need to be updated. But as long as it doesn't change, I can very efficiently do this whole occlusion culling thing, right? I can say, okay, well, if I'm here, only render that. So every room or every portal, in a sense, contains a list of things that are not occluded, that are visible. And that, of course, during runtime is very easy and very efficient. So we'll just basically load parts of that. And that's very often used in virtual environments. The question is this applicable all the time? All right, what happens if you have an open world? Okay. And that also answers the question, why didn't we have open worlds in the 80s or 90s in computer games? For exactly that reason, because they can't be portalized easily. Okay, so that's why all those games started in dungeons. Okay, so that's why Doom is in a dungeon, or Wolfenstein, or Unreal, or whatever, right? All of those games, Descent, they all started in dungeons to allow for this type of optimization. And that, as I said, that doesn't always work, right? If you're in a city, or if you're in a large, I don't know, jungle environment, you also have tons of occlusion. But the portals are so complicated, right? Holes in leaves or holes between cityscapes, right? That's so complicated that this optimization, despite its simplicity and efficiency, doesn't work. Okay, so it's a very important thing. Portal culling, it's still used today, and there's a ton of uses in the past. But how else can we? What's a general solution to that? And well, how do we do efficient occlusion and view frustum culling and other culling techniques as well? Yeah, as I said before, we use acceleration structures that I talked about before in the context of ray tracing, right? Remember ray tracing, I said, we don't want to follow those rays through the scene just blindly. We want to not check every object. We want to get a sub list of the objects that we need to look at. And one way was to use bounding volume hierarchies, and bounding volumes can be spheres, boxes, axis aligned, object aligned, or other things. Okay, and then we can turn them into a hierarchy. Here's a spherical hierarchy. And instead of checking the object with array, we'll just check the hierarchy. First check this sphere on the left. If that's missed, okay, we're done. If we hit it, then we'll traverse that hierarchy. And we can do the same thing for, say, culling to frustum culling to the frustum. Okay, so we'll just check the sphere. Okay, sphere to frustum is relatively easy, right? We'll just check how far is the center of the sphere away from all those planes. Okay, and then there's a few nasty nasty corner cases, but it's relatively straightforward for boxes as well. And only if that test succeeds, then we'll use the actual full resolution geometry. And again, we can do this through hierarchies. And it's got repetition here on the slide. This is verbatim the slide I copied it from before. Same is true. How do we construct those? Acceleration structures? Exactly the same. And we can do this axis aligned, object aligned. It's the same idea as we would do for ray tracing, maybe with like some different query mechanisms. Of course, ray tracing is kind of ray against structure or ray traversal. But again, if we do something such as occlusion culling, we again have a similar problem, right? It's like front to back, for instance, what we want to do. Okay, once something in the front covers something in the back, we stop. So you see that there's a lot of similarities to this idea of traversing a ray, despite not needing a ray if we rasterize this. Okay, and that's not to say that we can't ray trace a city, right? So if we ray trace a city, we would use them as they were before. Space partitioning, that was the other alternative, whether you use a uniform grid or a quad tree or an octree in 3D. That's what it looked like. Remember the animation that I showed you, what these octrees would look like if they grow. Here's the 2D view, one axis aligned, and here's the entire 3D view, right? Those are those octrees that basically put order into things. Instead of having this unstructured mess of things, triangles, or in this case, points, the advantage of these space partitioning structures was that they put order into things. Okay, so we could say, okay, well, let's first traverse the left and then the right, or let's look at the left. Or what happens if this entire area here is already outside the frustum? Well, then ignore it, ignore all the details. Okay, and the difference between those acceleration structures was it uniform grids, octrees, or the next thing that we looked at were BSPs, binary space partitioning, and then finally, right, remember my traversal order thing here, that's exactly what you need for occlusion culling. And then I finally looked at KD trees. So you see I'm skipping over this, well, because it's in the previous stream. Okay, the idea was really to put order into things to allow us to sort in a certain direction, which is exactly what you need for occlusion culling, or to reject parts of the scene, which is exactly what you need for frustum culling. Okay, so we can use the same structures with the same advantages and disadvantages. Okay, what were those advantages? Let's just summarize those. Well, the advantages were, well, once we've got this thing, you can answer a lot of questions very quickly, right? So there's a lot of things that we can answer in log time or in linear time. But what's the disadvantage? Well, what happens if the scene changes, right? How do we update these things? Because constructing these trees requires something in the order of n log n or so, right? So that's usually the best case because at some point we need to sort in general. And if we just do it from scratch, doing an n log n process over our entire data, we might as well render it because that's linear, right? So if we just render everything, that's n. And log n is obviously more complicated. So basically these things, octrees, KD trees, BSP trees, whatever you want to do, they only work very well if there's some assumption you can make on the structure of the world. Okay, either it doesn't change dramatically. You see, that could be change of my viewing direction or change of the scene itself. Or at least when there is a change, there's some way to predict it. It's going to have local impact, or it's a certain change. It's just an rigid motion or so, right? So what all this does, again, is it complicates the situation. It complicates the code. And again, coming back to my argument from before, why are scene graphs such a great idea? Because, well, someone can spend literally months working this out, integrating a scene graph, and you throw a few vertices at that scene graph, or a few billion vertices here, and it'll just magically handle that. Okay, and that's the key here. All of those things, acceleration structure, and also things such as parallelization, which I want to talk about just very briefly in the next few seconds or minutes. All those ideas, of course, you can implement it from scratch. I mean, someone implemented a scene graph from scratch, right? But just taking existing pieces of software, existing systems, might well be a lot more efficient than going from scratch because, well, some experts spend a lot of time getting this to work. So that said, a CF, as I pointed out last time, doesn't have to be slower, okay? And as a matter of fact, it usually isn't slower, right? If you take a big engine, I don't know, Unreal Engine, Lumberyard Engine, Unity, and put a bunch of vertices, put a big mesh into it, it's probably going to be faster than your first OpenGL attempt, right? Your first working OpenGL attempt, I should say, okay? But, well, it's probably not as flexible as your first OpenGL attempt, right? If you want to get some crazy new, I don't know, shadow approach into that one, it's probably a pain to get this into Unity, whereas if you got your prototype, it's probably very easy. And that was my other argument, that to maintain these pieces is hard. Okay, so last thing here, how else can we achieve performance? And that's basically, that's kind of the overkill situation, right? You could basically say, if all else fails, if any like smart technique fails, we can always throw more money at the problem. Okay, get a faster computer, right? It runs too slow, buy a better graphics card, right? I'm pretty sure you would get that answer from NVIDIA if you have a performance problem. But nonetheless, of course, there's a point where you could also argue theoretically, okay, we've reached the limit, so it's not possible to get better, or it's not feasible, not reasonable, would be too complicated, too hard to maintain. Then you can always try to parallelize. And that's exactly kind of the underlying concept of graphics cards themselves. Okay, so graphics cards don't do things fundamentally different than a CPU would do. The only fundamental difference is, well, which is a fundamental difference, I suppose. But anyways, the big difference is they are parallelized in a way that is not possible with general purpose computational units in a reasonable way. Okay, so graphics cards literally has thousands of processors that process the scene in parallel. And you can compare that to a data center where you have thousands and thousands or millions of systems or CPUs that process things in parallel, but shrunk to a small board. And the question now is, parallelization is one of those things that's, I would say, often said, and it's often easier said than done. So you could say, okay, we need this to be twice as fast, so just buy 2 computers, okay? So, and it's not that simple, right? It's not that simple because you end up with communication between the nodes, for instance. And there's just quickly here, there's these 3 strategies that I just called ABC here, okay? Specifically for graphics. And all these strategies are used. So strategy A, and that's probably the most simple one, easiest one, and that's the one that, despite being pretty bad, it actually works surprisingly well in reality. And the idea is just spend more money. Again, that would be, I guess, NVIDIA's favorite probably. And that's why they sell a solution that works this way. And same true for AMD, by the way. So I'm not bashing NVIDIA specifically. That's just the first name that comes to my mind. Same for AMD or Intel for that matter. So you just buy 2 graphics cards from whatever vendor. You buy 2 graphics cards and you send the entire scene to both graphics card, and you just render half of the fragments with one and the other half with the other one. Okay, and you could, for instance, render, I don't know, the top on one, the bottom on one, or left, right, or every odd or every even row, or every even pixel, or every even uneven odd pixel with one of the cards. So I mean, you could come up with a couple of ideas, but the basic idea is always the same. Okay, like, take the entire scene and break it into a screen partition, right? Left, right half, for instance, and then process half of the scene here and there. Okay, so what are the advantages? Let's first talk about those. And the one advantage is it's super simple. Okay, so it's super simple to do, right? Like, let's just take a very dumb approach, top bottom. Okay, so basically all I would have to do is submit 2 different viewports to the 2 graphics cards, and then collect the results, collect the pixel grids, and send them to a monitor. Okay, so today you would probably do this over the bus, but there are actually older solutions where you would literally route, say, the VGA signal from one device through the other, and one would write at the bottom part and the other one would write at the top part. So there's actually solutions that work in generator lock, Genlock, and they only process a few pieces. So apart from the wiring, then the communication is simple. Okay, so that's the advantage, but there's a ton of different disadvantages. So one is the first sentence here: store the entire scene in each processor. That is a pretty dumb idea because, well, you make incredibly bad use of your resources. If you buy 2 graphics cards, or 10 for that matter, you end up copying into every card the same scene. So you have 10 times the memory for 10 graphics cards, but you actually reduce it to once the memory. Okay, so you don't gain anything from the additional resources except performance. And that's the big disadvantage too, except performance. That is also questionable because, well, since I copy the entire scene to each and every of those devices, in particular when the performance is limited by, say, the vertices that need to be processed, still every card needs to process all the vertices in the scene. So we wouldn't gain anything. The only situation where you gain something is when the fragment processing is extremely expensive, right? Because every card only processes half of the fragments. Or you would have to have some efficient, say, for instance, frustum culling technique. If that's the case and you submit upper and lower part, then, well, frustum culling would give you part of the scene for the upper and part of the scene for the lower side, and then both could be quicker. However, in that case, who does that frustum culling? It's probably going to be the CPU, or the main processor of the system that figures this out. And that would quickly be overloaded because it would have to do multiple of these processes. Okay, so you might get a bottleneck somewhere else. And then the other issue is, like, when you would do this top-bottom distribution, what could easily happen is that one card has very little to do and the other one has a lot to do, and you need to wait for the worst of all of your distributed cards. So you would probably not do top-bottom, but like alternating line or so to make sure that the load is evenly balanced. And then the frustum culling wouldn't work. Okay, so long story short, it sounds like a pretty simple idea. It is a pretty simple idea. It's relatively straightforward. You can buy the solution. I think NVIDIA called it SLI, scanline interleave, and then later on, since it wasn't scanline interleave anymore, they just called it SLI. And AMD called this Crossfire, I guess. That was their solution. And I think they're still around. So you can, if you have too much money on the already overpriced graphics cards, you can spend even more money and get multiple of those. And for certain situations, get some speed up, but you waste a ton of memory. But it works. So the bottom line is, at least for those situations, it does work. Okay. Strategy B. What else can we do? Well, we can be smarter. Instead of distributing the screen, we can distribute the scene. We send half of the scene to one device and half to the other. Okay, that would be great. No wasted memory. Okay, everything is only stored once, except maybe for some overlap or whatever, but everything is stored only once. We can have a much better load balancing. Okay, we'll make sure that we submit about the same work to each card. And the big problem here is, like, how do we combine the results, right? If we have things that are in the front rendered by some of those hardware pieces, and there's things that are in the back, right, that are occluded by this here, how do we combine them? It's not impossible to do. In particular, for opaque objects, you end up with having to do a basically Z-buffer pass. Okay, for transparent objects, it gets nasty up to the point where it's almost impossible, right? If you got interleaved transparent objects, more on transparency in advanced image synthesis next semester. But if you get interleaved transparent objects, you need very sophisticated data structures, and then your final blending is so complicated that this becomes your bottleneck. So long story short, this works. It's used in certain environments, in particular for supercomputers, where you distribute things not just to a few cards in a computer, but to a whole cluster of computers. This is a very viable strategy, but this blend results together, this one simple sentence here at the bottom, can be extremely tricky, right? If you just think about this, you have a cluster of 1,000 machines, everyone generates a part of the scene, but not just a tile. It generates the entire scene, right? Let's say you want to render a 1,000 by 1,000 pixel image. So each and every of your nodes will generate 1,000 by 1,000 pixel images that need to be blended together. Now you can just do the math and figure out how much data needs to be sent for this to be blended together. Now, say you want your visualization at, I don't know, 50 Hertz, you can easily figure out at what point your entire network is overloaded, regardless of how much money you spend on the network. So in that case, you probably need a hierarchical solution. Long story short, that's a nice topic for a parallelization lecture. But bottom line is, it's technically a better idea, but the realization is very, or can be very complex. And then there's the third strategy that I call strategy C here, which is kind of the most complicated, but potentially the best idea, but with a bunch of drawbacks attached to it by itself. And that's divide the process into a pipeline, basically into different tasks, and process parts of that in a pipeline fashion. So this is again something that is not specific to graphics and that is not particularly new. I mean, look at processors; they have very deep pipelines. But you can look at things like the Pentium 4, and then you already get the idea where pipelines fail, right? If they are very deep, very long, they also introduce issues. Latency, in the case for the Pentium 4, prediction problems. But anyways, the idea of a pipeline is a very nice, allows for very nice parallelization. So say we have three CPUs here, or 3 systems that can process data, okay? And let's say we can break our process of image creation into multiple steps that need to be executed one after the other. Pipeline. Okay, so that's exactly what a pipeline is. And I just call them app, cull, and draw here. So for instance, first of all, we need to do some app processing. That is, I don't know, check users input, let monster explode when it's hit by bomb or whatever. So that's just general kind of environment around that takes care of the image generation or takes care of the data that then needs to be visualized. So the next step that I said could be culling, right? View for some culling, occlusion culling, and that potentially takes some time, right? Traverse your data structure, maybe update your acceleration structure, and then ultimately rendering. Each of those steps, of course, could be broken down further, but I'll just want to keep it simple here. So then what I could do is I could have, like, if I just want to use one CPU, it would execute the application-specific part for the first frame, would execute the culling for the first frame, and then would execute the drawing for the first frame. Instead, I could just do the application-specific stuff on CPU 1, submit the results, which are hopefully, important thing here, hopefully not big, don't overload the network, but can quickly be shot to the next processor. And then that does the culling. And in the meantime, my processor 1 is idle, and it can process the next frame. Okay, once the culling is done, the processor submits it to a third processor that does the drawing, say the graphics card, that does the drawing, and it's idle itself, so it can take the results from the second app pass from the first processor while that one does app 3. So long story short, what you will see is that regardless of your depth of the pipeline, except for some initial latency, we will spit out 1 frame each time slot. Okay, so regardless of, like, if I break this down into 100 steps, where each step probably only takes very short amount of time, right? And I have 100 processors, like every time step, I'll generate 1 image. So I get 100 times speed up, which is great. Okay, so, but here are the buts. Big one is, we need to send the data. Second one is, before we see frame 1, or in the moment where we see frame 1, we already need to be able to process frame 3. So that means we have a latency. So for instance, if this app-specific stuff depends on the user's input, whatever your input will be pipeline depth away from what you see. That might be tolerable or not. So you already see that there are situations where this works better or where this doesn't work. Okay? Same is true, by the way, for some of those acceleration methods of strategy A. So one thing that you can do is, instead of top-bottom screen, you can do odd-even frame. Like one card can process the even frame, one the odd frame, and just send one after the other. So again, that gives you speed ups. Well, that doubles the performance, but it also doubles your latency. Whether that's good or bad probably depends a lot on the specific scenario, right? So those are 3 strategies, A, B, and C, and gives you an idea that parallelization is, well, easier said than potentially done. And since it's very specific, some of those drawbacks and advantages are very specific. There are situations where one works and the other doesn't. Okay, do we have any questions? Actually, chat is awfully quiet today. So, chat still working? Yes, it is. Okay. You're welcome. Okay. So at least the chat is working. We know that one. Okay, good. Then final thing. So before the stream is over for good, let's just hope that we'll have lectures in present back next semester. Let's just talk about one final thing here. And that is sampling. And that is, like, if I just want to recapture a little bit, what have I talked about both in presence at the beginning of the semester and then in the last couple of streams here online in distance learning. I talked about things such as ray tracing or rasterizations or rendering approaches. I talked about a couple of ingredients that we need, right? How do we model things? How do we transform? What's this shading and lighting thing? What are textures? Remember textures, the whole fire thing? And then I talked about acceleration, both in the context of ray tracing or general rendering, and then in terms of scene graphs, and talk about low and high level API. So that's basically what I covered so far. And with all that knowledge, you can go ahead and implement multiple rendering modes. I mean, at least ray tracing and rasterization approaches, you could do that, assuming that you've fully understood all the stuff that I said. Okay. So what else needs to be done? So what's the future? What's the rest of today? So what I want to talk about a little bit is aliasing, and well, how do we counter that? How does anti-aliasing work? Okay, so a quick side note, because this is a German stream, you know aliasing, okay? Please don't call this aliasing or something. Hey, it's alien, everyone pronounces alien correct, aliasing, okay? So remember that guy, you get it right. Okay, so what is all of that, what do aliens, so apparently it's got something to do with that. What does that have to do with computer graphics? I know aliens are very popular in computer graphics, but what's the point of aliens? Okay, for that, I need to very briefly touch on signal theory here. And colleagues that electrical engineering or multimedia colleagues will hopefully excuse that I do this in a very rough fashion, okay? So this is just a quick tour, just touching the surface. But anyways, okay, so we need to talk about something that's called sampling. Okay, so what's sampling anyways? It's a pretty simple thing. So what we have is we usually have a continuous signal in some way or another. What do I mean by usually? I mean, the world is continuous. Again, forget quantum dynamics here. We do this in advanced image synthesis a little bit, but here, no quantum dynamics, everything is continuous, okay? So we've got a continuous world. We've got a continuous height field. Let's say the red line here is a cross section through a mountain range, okay? We got a continuous motion of an object. We got a continuous sound. So a ton of things that kind of exist in a continuous fashion. And this continuity is not the thing that computers like that much, okay? So what we usually have is we have some discrete representation, okay? Despite that discrete representation being a proxy for a continuous thing, okay? And we should not forget this. This is very important. So what is sampling? Sampling is simply figuring out at certain places or time steps, I put this here in the context of time, but the same is true for places, figuring out what this continuous thing, whatever the thing is at those time steps. So at time 0, the height of this height field at a specific point, say it's a wave, right? It's I don't know, it's a water wave, it's literally a water surface, okay? And it bounces up and down at some point. At time step t0, when I start my clock, we've got a certain height. And then t, let's say it's 1 second. 1 second later, I've got another height. 2 seconds later, I got another height, so on and so forth. And this process of reading a continuous signal or reading a signal, and that's called sampling. Okay, now what does sampling and what do aliens have to do with computer graphics? Okay, here's the thing. Image synthesis, let's get out of the way, is nothing but a point sampling of a continuous signal. So what do I mean? Well, your image, what is your image on screen? Your image on screen today was different in the past, but today you're all sitting in front of a raster display. Okay, so you're sitting in front of a display that is a bunch of points. It's made of a bunch of points, we call them pixels, and that is your window through a continuous world. So image synthesis is really nothing but figuring out what is usually the color or the brightness for a black and white scenario. What's the value at certain points of a continuous world? So all we do is sampling, right? You could argue, probably some colleagues would do this in electrical engineering. They would say, well, all the computer graphics is just point sampling the world. Well, yeah, and it's even true. Okay, so an image is really just a bunch of discrete positions, the finite set, I don't know, 1024 by 768 or so, regularly sampled points. Okay, and there's a bunch of trivial implications of that one, right? I mean, your pixel spacing, the resolution of your screen, that shows you or that determines how well you can handle the world. More pixels, more resolution, better quality. As simple as that, right? I don't think that requires any further explanation. What's interesting here is kind of the opposite. Again, it's trivial, but the implications aren't so trivial, okay? So the obvious other situation, again, let's get out of the way here, is that, well, if my resolution is insufficient, parts are lost. All right, it's as simple as that. Don't have enough pixels and things are small, they're probably going to vanish. Okay, and we call this aliasing. Okay, this process of losing, or better said, of introducing wrong results in the reconstruction process, that's called aliasing. What's reconstruction? Okay, like, here's the thing. Again, the world's continuous. Okay, let's just take that for granted. The pixel grid on your screen is discrete, right? You've got discrete pixels. Now, here's the thing. Your screen doesn't have holes, right? I mean, if you take your screen, I don't know, your monitor, it's a continuous surface, right? I mean, if you touch that, it's a continuous surface, so it doesn't have holes. Despite the fact that we treat this as a discrete grid, right? We assign some data to pixel 1, we assign some data to pixel 2, and so on and so forth. The thing itself, again, is continuous, right? The monitor is continuous. We just can't access or can't drive it in a continuous fashion. And that's reconstruction. So we've got this awkward situation that you hardly ever think about, but that's the case, right? We've got a continuous world that we want to render. We turn that into a discrete structure, right? Either by taking a photograph with a digital camera or by rendering it, doesn't matter. And then we apply that in a discrete fashion to a continuous surface. Right, as I said, your screen doesn't have holes, right? It's a continuous surface again. And even if it's not continuous, right, think about LED projection like in a stadium where we literally have holes between the LEDs. From your viewing distance, it's generally continuous again. So then you could argue that the reconstruction, and that is recreating that this continuity happens in your visual system, right? At some point, it's going to be continuous. So, and that's the reconstruction. So it's a three-step process: continuous signal, discrete intermediate, continuous end result, right? And that last step is often forgotten, but it's very important, okay? Because what happens is that we do sampling. That is the process, taking the continuous signal into a discrete fashion. But we don't just take these samples. We turn that discrete sample structure back into a continuous structure, okay? I think I talked about this way too much, but it's very important because this is often forgotten. Now, in this last process, in the reconstruction, in this filling of space, we introduce structures that aren't there, potentially, okay? Simple examples, staircasing, right? If you have a diagonal line at very low resolution, what you will get are staircases, okay? So your reconstructed line doesn't have holes, right? I mean, it's blocky, but it's like every point on screen that I can point at, I'll touch something, right? So I basically add new detail. I add this staircasing that wasn't there in the original signal. Okay? So I've got two continuous signals and they're different. And that's what's called an alias. So we suddenly have something, or ghost. Alias is really synonymous to ghost, right? So we have a ghost signal. We have the stairs that isn't in the original signal that we suddenly created in this process of sampling and reconstruction. Okay, that's what aliasing is all about. So here's an example. I guess it's pretty obvious, but so let's go through some examples to understand the process a little bit better and then to counter it in some reasonable way. So we've got an image here. I mean, we're doing computer graphics after all. We've got an image here. We've got a still image here. We've got these grapes in a bowl and fruits. And now let's just take this one line here. To simplify things, I want to do everything in 1D. Okay, so we take this one yellow line, and at the bottom you see that's just the brightness distribution of this line. Okay, so it's black, it's 0 at the beginning and end, right? And then we've got this bowl in itself and gets brighter towards the center. So along this line we got an increasing brightness distribution, and then come the grapes, and we've got this ups and downs. Okay, so that's our pretty much continuous signal here. Okay, despite the limited image resolution. Okay, let's say, but in reality, that's a continuous signal. Okay, now I sample that. Okay, so I take a rendering approach and I sample that at the top in 2D and the bottom in 1D. So now what you see at the bottom, those are my samples. Now if I apply them to a pixel screen, right, both in 2D or 1D, here we go. So that would be my pixel screen at the top and the signal at the bottom. Okay, so that's my luminance, brightness signal here at the bottom. And you can see that it's different. No big deal. Here's the same, again, for a more simple signal, right? We've got this wavy pattern. I discretize that and I display it as discrete pixels. Okay, and voila, we've got staircases that weren't in the original. And it can get even worse. Okay, here's another example. Right, there's a signal on the left, so that's an awkward picture, but nonetheless, it's on the left, and here's the reconstruction. Notice the bottom red bar is completely gone. Some of those teeth are gone, and some of those, well, I don't know, yellow triangles in the center are blown up in size, right? And they should be symmetric, but one is smaller, one is bigger. And now imagine I shift my pixel grid around, so meaning I might turn my camera around. So like, for instance, moving the pixel grid down or the scene up will suddenly make this red part appear here. So you can see that, well, we lose detail. Okay, and the question is, does that always have to happen? Do we have to lose detail? Is there really nothing we can do about this? And yeah, well, if there's something, what can we do? And the answer is, yeah, we can do something about it. Okay, but it's actually tricky. It's actually particularly tricky in computer graphics. And what you can see is that there seems to be some sort of relation between the size of a structure and the problem. Okay, so if I would increase the size of the structure, so make the red, green, and orange things here, yellow and orange things bigger, it would probably not be such a big deal here. Or if I make my sampling rate smaller, so I do more samples, I'll also get a better image. Right? So there seems to be some relation between the sampling rate and the structure size that describes the level of problems that we run into. Okay? And there's another issue that is related to this. That is this ratio between size and sampling, structure size and sampling size. That is very tricky in computer graphics scenarios. Okay, so because you could say, well, increase the resolution and you'd be better. Well, here's the thing. If I look at something in a perspective setting, right, so where things further away are smaller, then the same object, depending on where it is at different distances, and these distances change, I mean, I change my camera around, will be different, right? I mean, here's a simple example, shown this a bunch of times before. We've got a simple theme, checkerboard pattern at the bottom, okay? We sample that at the front, it's pretty okay, except for some aliasing issue here. But at the back, we just get random mess, right? We get circular structures, we get stripe structures, so it's pretty much random what we get towards the back, right? And so the sampling rate is, of course, usually constant on screen. So most screens, if not all screens, have constant distance between pixels, right? But in the space of the scene, right, the world space, this sampling rate can vary significantly, right? We have a relatively high sampling rate here, but the sampling rate is obviously too low. Yeah, so, and that makes things very tricky, in particular in computer graphics when it comes to sampling rate, that we've got this non-uniform sampling. Okay, so of course I can't give a lecture on sampling without at least citing Shannon's sampling theorem. And that's that's a little bit more specific than what I said before. So before I said, okay, there seems to be some sort of relation between our pixel resolution, sampling rate, and the signal, structure size. And Shannon is a bit more specific. So he says, or he said, the signal has to be sampled at the frequency that is equal or higher than 2 times the highest frequency in the signal. Okay, so that's kind of similar to what I said before. Objects are small, we need more pixels. Okay, but this is more specific, as it says, okay, we need 2 times the pixel. Now, or at least 2 times the pixel. Now, one thing that is very awkward here is, or that you should realize that is awkward, is like what's it with the highest frequency in the signal? Okay, I mean, signal is fine, right? I mean, you can draw this graph in 1D, but what the hell is the frequency of a bunny, right? An image of a bunny, right? Or the frequency of, I don't know, New York, right? What's it supposed to mean? Like, what's this term, this terminology that comes from signal processing, from electrical engineering or engineering? How does that apply to computer graphics? Okay, more on that in a second. Let's first look at this here, at this whole, at sort of the grounding theory, or the grounding practice more, to Shannon's sampling theorem. And for that, I would just want to show you the simple image here. I think I grabbed it from Wikipedia, and I guess it just depicts the problem nicely. Let's go from bottom to the top. So what we do here from bottom to the top is we increase the signal's frequency. Okay, so in this case, the signal, I said signal can be very tricky in computer graphics, but let's be simple here. Okay, our signal is simply a sine wave, or, well, if that's x-axis, it's probably a cosine wave, but it doesn't matter. Okay, it's a wave that oscillates up and down, and for such a simple wave, frequency kind of makes sense. Okay, so that's the difference between, or the wavelength is the difference between up and down, and frequency is 1/wavelength. Okay, so that's trivial. If I increase the frequency, well, the wave gets squished together. Okay, so we've got a wave at the top, and then you can see the wave gets smaller and smaller towards the bottom. Now, the other thing that's in this image here are these little lines here with the dots. So those are our samples. Okay, and again, look only at the top here for a start. So you see we've got our signal at the top, we've got this sine wave, and I take a bunch of samples. I take actually a lot of samples. Okay, and what I can do is, once I've taken those samples, I can take just the sample data, just like this set of discrete points. I can take that set of discrete points and recreate the exact wave. I mean, I don't have to do this in a jagged fashion, right? I mean, I can say, okay, well, draw me a cosine wave that goes through all of these points, and I'll get the exact same result. Okay. By the way, that's just a side remark, because people get this. It's so annoying how people get this wrong. That's, if you think about sound, right, for a second, think about the CD. That is also sampled, right? That's a sampled signal, and it fits this idea here a little bit better because it's a one-dimensional signal, right? It's just the waveform. And a lot of people think, oh, Jesus, digital sound is so bad because it creates these jagged edges in the sound. Of course, no way. But of course, what you do is if you run this through an amplifier, if you turn this into an analog signal and run this through a speaker, of course you take the sample and you create the smooth waveforms. Okay, there's no jagged waveforms in digital sound processing. Okay, so, and that's very important to remember. Like, A, if you bash CDs, which is completely stupid, okay, but B, if you think about digital processing, the end result, the reconstructed continuous thing, be this a picture on the screen, or be this a pressure distribution from your speaker, we call music or sound, right? That's, of course, again, a continuous signal. Okay, we've reconstructed the continuous thing. We're not stuck with this jagged edges situation. Now, if I take, according to Shannon's sampling theorem, if I take twice as much, at least twice as much samples as the wavelength, I'll be able to reconstruct exactly the original signal, no loss whatsoever. Okay, and we can see this here. So there's only one sine wave or cosine wave that passes through these points. So there's no ambiguities. Now what happens if I slowly increase the frequency? So it'll work for the first 5 situations. Up to this point where I have like all the ups and downs sampled. Okay, which is exactly the situation where I have twice the sampling frequency. So I do 2 samples per wave, per oscillation. Now, what happens if I drop below that sampling scheme, or if my frequency increases. So, and that's the situation here. Now it gets interesting. As soon as I as I increase the frequency further, there's suddenly two signals. Okay, there's the original dashed signal that of course fits those points perfectly. I mean, I read it from the original signal, so they, unless I make a mistake in the measuring process, which I of course do, but let's ignore that here. Okay, so if I measure the original signal correctly, of course a reconstruction is still plausible, the original signal, but there's a second cosine wave, and that's the dashed line here, that also perfectly fits through these points. So at that point, if I try to reconstruct this, I have two signals that are equally likely. They fit this perfectly, and I have to pick one. Okay. Now, you could say, okay, well, there's a 50-50 chance I pick the right one. But no, usually there's a 0 chance I pick the right one, because you always want to pick the one with the lowest possible frequency. Why? Because, well, to be honest, of course, the top signal also, the top samples also have an infinite amount of signals that pass through these points. I mean, there's super high frequency signals that also pass through these points. So I always have to make a choice. And you normally want to pick the one that has the lowest possible frequency. And here, the one that I would pick with the lowest possible frequency is the wrong one. That is my ghost signal. That is my aliasing signal. That is my other signal that I didn't want to pick up, but I suddenly have. Okay, so that's also where the term aliasing ghosting comes from. Okay, so I created a ghost that I don't want to have. Okay, another continuous, not jagged signal that's there. Now, and here's another nasty thing. The higher the frequency goes, so if I increase my frequency higher and higher and higher, you see that the variation, the difference between my signal and the ghost that I created increases. So the higher I make my frequency, I mean, here really the two signals have nothing in common anymore. I got this very like slowly varying signal here that I reconstruct, and I get this super high frequency signal that I initially had. Okay, so and that's what sampling is, and that's what reconstruction is, and that's, from this point on, is what aliasing is. Okay, and it happens every time you sample, right? Or it can happen every time you sample. Okay? And again, a very important fact is, if you stay below the Shannon frequency, if your frequency is smaller than twice the sampling frequency, you have no loss. Theoretically, no loss. Of course, practically no loss, unless you count measuring issues, right? But those will always happen, right? So in theory, even in theory, you have no loss, so stop bashing CDs. So they reconstruct the exact original signal, okay? At least in the area where you can hear. So, and the same is true for computer graphics, just in 2D. Except that in computer graphics, we generally do a pointwise reconstruction, okay? So this is where those jagged edges come from, since we pointwise reconstruct, which is in the nature of a display, right? A display is a pointwise device. Or these days, it's a pointwise device, right? So if you go back into the 70s, you had vector displays, okay? So in that case, you could actually reconstruct diagonal lines without jagged edges, because you would just drive the electron beam appropriately. So, but that's a different issue that comes on top of the sampling. That is that our reconstruction device in terms of screens is very limited. Okay. Now that's what aliasing is. Now let's talk about anti-aliasing. So okay, that sucks, right? And that we get the wrong signal is bad. Like what do we do against it? Okay, and the solutions are like super trivial. Okay, first one is, well, if the sampling frequency is too small, pick a bigger sampling frequency. I mean, dumbass, right? So literally, like, if your frequency is too small, why don't you choose a bigger frequency? Okay, so that's solution one. Okay, and we'll see in a second if that's such a simple idea or not. The next one is, well, if your signal has too high in frequency, well, decrease the frequency of the signal, right? So that's the second solution, okay? So that's what we call pre-filtering. So we remove parts of the signal. So we change our signal, we change our scene. So to what would this relate? Of course, super sampling is buy a better graphics card, buy a better monitor, right? So what does pre-filtering count to? It's like, okay, well, don't render that scene. Like if it's got too much detail for your monitor, right? Don't render that scene. It's your fault, right? You didn't buy a more expensive monitor. Okay, so that's kind of solution 2. And then there's solution 3 is like, okay, we messed up it, but let's at least hide it so that no one sees it. Okay, so that's kind of solution 3, which we call post-filtering. Okay, so we've got a bad signal, it's all aliasing, but let's just mess it up so much that no one can see the problem. Okay, so those are 3 solutions to the problem. Well, okay, let's briefly talk about those. Okay, super sampling. I said buy a better monitor. Now, admittedly, that's probably directly related to the amount of money that you have available, and you potentially don't have a bigger solution. Even if you have all the money in the world, maybe you can't buy a better monitor because you bought the most expensive one already. Okay, so what else can we do? And one other thing that we can do is, well, we don't have to render, or take the photograph. That's the same situation, really, if the digital photograph or a rendered image. We don't have to bind that to the monitor resolution, right? So if you, for instance, take a photograph, even with your cell phone these days, the resolution is so incredibly high. It's usually way higher than your monitor's resolution. So you have to zoom in before you see anything. Like see any aliasing artifacts, right? See pixels or so. So one thing is to just say, okay, well, I don't want to buy a bigger monitor. I can't, for whatever reason. But let's just do the image acquisition process, be this camera or be this rendering. Let's do that at higher resolution. Okay, sure, that's good. We increased the resolution, we avoided or at least reduced aliasing in that process, but we're still stuck with the same monitor, right? We're still stuck with the same, cell phone screen, smartwatch screen, projector screen. We're still stuck with that. So what do we do? And that's kind of where this post-filtering idea comes into place, okay? So we could say, okay, well, sure, we got this signal now in discrete format, but it's too high resolution. So let's just filter it out. So what we could do is, for instance, just a simple example, we could super sample, say, 4x4 pixels per pixel on screen, okay? So we just take 16 samples, which is, 4 times higher resolution in every direction. And then we somehow need to break these 16 samples down into one, so we could just average it out. So we just take the average of those 16 values and we display that on screen, okay? So that is not super sampling per se. So super sampling is this process of creating more samples. That's what this means. It's Latin super, more, higher than the previous testing. Sampling is just checking, okay? But this, what it does is, once you reconstruct this, you somehow have to work with those super samples, and one way is to compute the average, okay? And here I just simply call this alias and anti-alias. So you see on the left, or here on the top bottom, let's stick with this image here first, right? On the left you see rendered at screen resolution, and zoom in, you see the obvious jagged edges of this diagonal block. If I take a higher resolution rendering approach, I'll have some of those super sampled, let's take these here, some of those super sampled will end up in the background black, some will hit the object white. If I compute the average, I get, gray. So I get a washed out situation here, and that effectively hides some of the aliasing. Okay, same applies here, right? So if you look at the boundary of that sphere, the top, if you zoom in close, you still see the same kind of pixel structure, right? But this one here looks, in particular and small, looks much worse because, those issues are blurred out. Okay. Notice, however, that if you think about a signal, like if you think about an actual signal, right? What was this sphere? Well, in particular, the boundary of a sphere was a sharp edge, right? We have a drop from, say, white is 1 and black is 0. We have a drop from 1 to 0. So we have this kind of step staircasing pattern in the original signal, in the original continuous signal. Our reconstructed signal now is smoothed out, right? So this here looks more like a curve. Okay, so we're still making some sort of error here in a reconstruction process, right? But the key is, and that's often the key in computer graphics, and I've mentioned this a couple of times throughout the stream here, not today, but throughout the entire stream, is it's often not about getting things right, but getting things unnoticeable. Okay, so in particular for scenarios such as, games, virtual environments, any experience really, it's not so much, or in some cases, right? There are cases where this would be an issue, but in many cases, it's not so much about getting things right. getting things unnoticeable is just as good. If we can't tell the difference, it's perfectly fine. At least in some scenarios, right? Particularly counterexamples are visualizations, for instance, right? If I render, I don't know, I render a, let's say, I render a CT scan of a brain, and well, I don't see as a surgeon, I don't see the cancer tumor, but it looks pretty realistic. That's not okay, right? I want to see every detail. It's got to be there, and it's not about getting a realistic depiction of the brain. I want to get like the depiction of that particular patient's brain. And even if the tumor is small, I want to see it, right? And if it alias, if it flickers, even better, then it'll probably guide my attention to it. Okay, so there are limits to this approach. But again, there's often the situation that it's that indistinguishable is good enough. Okay, so and now the question is, and again, the devil's in the detail. The question is, where do I put these super samples, right? I mean, the most simple approach is like, whoa, the problem, right? I mean, you want to have 2 by 2 samples per pixel. Okay, let's do them here. 1, 2, 3, 4, done, right? That's what we call regular super sampling. Here it is. That's what it looks, right? We now have 2 by 2, which makes a total of 4 samples, well, it looks pretty good. Now, what happens if I say 3 by 3? Say okay. Well, now 3 by 3, that's an odd number. Now they have different distances to the center, right? So we could say, okay, well, the one that's in the center, let's make this more important, right? Let's weight this by 1/4, 1/4, 1/4, Jesus, 1/4 or 1/4, 1/4, and the ones that are further away, 1/16. By the way, all this sums up to 1, hopefully. Right? I mean, it does, right? So as soon as you have more samples, either odd samples, or even if it's more than 2 by 2, you also have different distances to the center. You can say, well, I mean, the center should count more, right? It should be more important. So we'll probably weight that more when we average this out. Okay, here's an example of 5 by 5. Okay, or it's actually sorry, it's not 5, it's 3 by 3, but it's 4 times 3 by 3. Okay, so here's on the left, you see the high resolution version. Okay, so this is what the samples see, and then if we combine every 3 by 3 to one color, we'll get the situation here. Okay, so this is then my reconstructed point sampled version of the point sampled higher resolution sample signal. Okay, now there's one issue with that approach, okay, be it this weighted or unweighted approach where we consider everything the same, and that is the human. Okay, so there's always the human in computer graphics. One other take-home message is it's always the human that messes things around, that makes things complicated. Okay, so physics, it's all fine, engineers all fine, humans mess things up. So what's the problem here with humans now? The problems with humans is that we're pretty good wired. So we have specific hardware, like literally hardware in the visual system, in the brain, and also in the retina already, to detect edges. So we've got this damned hardware. It's very important, by the way. So it's very important for our perception. But we've got this hardware in there that enhances edges way beyond their actual structure. So okay, so if there's an edge somewhere that we see, our brain points us to and says, oh, okay, here's the edge, or please don't bump into that one, or this is, I don't know, this is saber-tooth tiger, run away. I don't know, right? I mean, you can obviously see the point. And since we are so good at detecting edges, any edge that's in some data in a scene will be highlighted way beyond its actual value. Okay, so if we have a regular pattern and we have a structure, then anything that any difference in value will have some regularity in it, right? I mean, if we see so like this pixel will just barely catch that one, and this here as well will barely catch the other side. So any structure will be axis aligned. It will create lines, will create edges. Okay, and we're so good at that it will see that. Well, that'll create structure that we'll notice. To kind of fool our human visual system, to get things better, we can do what's called jittered sampling. So instead of having those samples to be evenly, uniformly distributed, we'll add noise to their position. Okay, and you can even change that temporally, but let's just stay with fixed noise. Let's just say we slightly jitter those positions. So what that does is it creates noise in the final image. If you add noise to the sampling process, you'll have noise in the result. Okay, so that's again something that is probably trivial, but that's very often overlooked. Adding noise in the sampling process adds noise to the result. As simple as that. If I jitter those points around, right? If I keep the image fixed and I would jitter those points around, depending whether, say, let's just focus on this one here, whether that point is here or there, will either catch orange or catch red, and that will of course have an impact on the entire pixel. Since it's a center pixel, and when we do some weighting, it probably have 1/4 impact on the entire pixel. So that thing will flicker. And the same is true if I tilt the camera. So jittering in the input will create noise in the output. But it will get rid of these regularities. Okay, all of those regular lines that we might have seen here will now be noisy. Now, for once, the messy human visual system comes to the rescue because it does two things. Well, there's a ton of things, but one thing I already mentioned is it enhances edges. Another thing it does, it represses noise. Okay, so any acquisition process, any measuring tool, be this a technical device, I don't know, a thermometer or whatever, any measuring tool adds noise to the signal. So there's no perfect measurement. There will always be issues in the measurement, okay? And the same is true for biological measurement. So our receptors will add noise, and there's a ton of reasons for that noise. Okay, so there's ADP being required to be pumped into your neurons, to your cells, right? You've got oversaturation. So there's a ton of things, right? I mean, I talked about some of those in the color literature: temporal aliasing, temporal effects, spatial effects, oversaturation. So there's a ton of things. But the point is, there's noise in the acquisition, there's noise in the human visual system, and evolution countered that by simply suppressing the noise. I mean, it would be pretty annoying if I would look, it would probably drive me mad if I look around here somewhere and I would see all the noisy effects of my visual system, of my eyes, of my retina. So noise is suppressed, and that's cool because now we've added the noise to get rid of the regular structures, and that works, but the noise is suppressed, so it's gone. So that's sort of the motivation behind jittered sampling, right? It adds something that's suppressed by you instead of being enhanced. Okay. Now, the funny thing is, again, it's easier said than done. How do we want to stochastically place those samples? Okay. So here's just a few examples. Okay. So what does it mean to jitter things a little bit, right? And so one very elaborate thing would be Poisson disk sampling. Okay. So we could just start to place our samples, as many as we want, in our area. So they should still be underneath a pixel, I suppose. And we could just place one and then make sure that the next one we place is at least a certain distance away, and the next one is at least a certain distance away, and then we fill space. You can imagine that probably is a numerically complicated process. It takes some time. A more simple approach would be, okay, well, let's start with the regular spacing here, right? Let's start with the regular spacing and just roll a few dice and compute a vector. Just compute a 2D vector, right? Two numbers, and that if it's small enough, we'll just displace each and every point by that vector. Okay. Notice that has some limitations. For instance, 2 points might be awfully close together just by coincidence, or there's certain areas where we can't reach or shouldn't reach, right? From that point on, we can never move that point to the top right. Okay. Yet another approach is that we subdivide our pixel, say 2 by 2, if we want to do that, and just compute a random position within each of those cells. Okay. Again, that doesn't guarantee uniform distances, but it's at least fast. It can be computed pretty quickly, and that's assuming that we would really vary that all the time. Okay, because then it matters how long it takes to compute. Another approach would be to just pre-compute that. Okay, so just do a Poisson disk sampling ahead of time. Maybe do 10 of those, or 100, or 1,000,000 of those, and just pick one from an array. Right, that's another feasible solution, and that gets around the issue of how long does it take to compute that. My point here is just, and there's other solutions as well. My point is just like jittering things is is not just a one sentence thing, right? So you have to, like, it's one sentence, but it requires some more thoughts to get this to work. Okay, so what does that look like? Here's an example. Okay, so here is an example that shows exactly what I said before, the fact that our brain highlights certain structures and suppresses certain structures. Okay, so what we've got here is the same scene, so it's a slightly tilted quadrilateral at 1 by 1, 3 by 3, 7 by 7, 3 by 3, 7 by 7, whereas the last two are jittered samples. Okay, so now the first one is regular, you see a ton of aliasing, and the next one is 3 by 3 regular super sampling. You still see the staircases nicely. Okay, and I mean, it's more steps and it's somewhat smoother, but it's there, and that's exactly your brain overly exaggerating that. At 7 by 7 you can still clearly see, unless the codec eats it up, but it shouldn't too much. You can still clearly see the steps. Now, if I do jittered sampling, as I said, input noise, output noise, so the result will be noisy. Okay, so you'll have noise here, right? You'll also have noise here, but it's noise over the same value, so it doesn't matter. But you see the noise here, okay? And if you look very closely, you can see the noise here, and that's exactly my point, right? From a performance point of view, this is about the same. This costs about the same time to compute as this one here, but it's much harder to tell either the noise or the staircases. Okay, and that's exactly what jittered sampling gives you, jittered super sampling. Okay, here's a set of 2D examples. Let's get out of the way. That's again the still with the bowl and the grapes. Simple resolution, no anti-aliasing. Notice there's particularly in the back, I've zoomed into area, complete nonsense here. Let's do 3 by 3 super sampling and a 3 by 3 unweighted filter. Excuse me. So that means we now do 9 samples per pixel and just sum them up and divide by 9. Okay, unweighted, all the same. Okay, get somewhat better. Compare this one here to that one, right? In particular, if you look at the entire image here first, you see like this creates strange patterns, right? Look at the right underneath that worm. You see that there's like spherical patterns, and well, they're gone. Well, at least to some degree gone. They're still there, but they start to disappear because they get smaller, right? You have more of these rings, and they're not that noticeable anymore, but still there. Okay, increasing the sampling, not increasing the sampling. That's my key here. Not increasing. I'm still doing 3 by 3, but now jittered sampling, and a 5 by 5 weighted filter. And well, I would argue that it, in particular, on the whole image, it gets I would say it gets significantly better, because again we trade structure for noise, right? It gets somewhat more noisy. Now the question is, how can I do a 5 by 5 filter if I only have 3 by 3 values? And the simple answer is overlap. So I just take values from neighboring pixels and include them into the computation. Okay, so that's another trick that you can do. I don't want to talk about the theory here of that one, so we can look at the theory. Electrical engineering, we'll do that. We can also do this in advanced image synthesis a little bit, but there's all of those tricks have certain implications on the reconstruction quality. But probably come back here, but nonetheless, there are ways to save some performance, get more values than you would initially expect with a relatively small overhead, and increase the quality, at least in some situations. I mean, the favorite acceleration technique that has been used in the past when graphics cards were a lot slower than they are now was to just do 2 samples, one in the center and one in the, say, top right corner, which if you're raster bound, so if your fragment amount is responsible for your performance, which halves your performance. Let's say that's tolerable. Let's say you had 1,000 hertz and now you're at 500 hertz. So that's tolerable. So you get 2 samples, and they're kind of awkwardly spaced, right? One in the center, one in the top right. But if you take the top right, notice that the from the pixel here, its top right is my bottom left. Okay, and this pixel here, its top right is my bottom right, and so on and so forth. So basically, looking at the neighbors, ignoring the boundary for a second, looking at the neighbors, I can get at twice the performance cost. I can get 5 samples. And that's one of those tricks. It's called Quinn-Cook's sampling, because it resembles the shape of the 5 on a die. And it gives you 5 samples at just the cost of 2. Since the samples are reused, again, you need to look carefully at the theory. It's not 5 times, or it's not 5 times better, whatever that means. But nonetheless, it sort of gives you 5 samples in the vicinity of your pixel at just half the cost. So there's a whole lot of theory, sampling theory, that it takes to understand the details. But I guess the overall theme is clear. Okay. So what was the overall theme? Signals to high frequency. Well, increase your frequency, increase your sampling frequency. Now let's just quickly look at the other solutions. Decrease the sampling frequency. You don't want to increase the frequency, or you can't. So what else can you do? Well, change the signal. Okay, here's an example for a picture. Let me start with a picture. Right, we have a photograph. I can reduce the resolution of that photograph by smoothing it out. Or I don't even need to reduce the resolution, just reduce the signal, right? Let's say I keep the original resolution, but I smooth it out, okay? I smooth out the image so that what happens? High frequency variations in the images are gone. How do I smooth things out? There's a ton of filters. I talk about those in scientific visualization. There's median, mean, box filter, Gaussian filter. So there's a couple of things, but I guess you'll probably believe me that it's possible to smooth things out, right? So, and now if I would render that image here, well, it doesn't alias anymore. Now, same problem as before. What do I mean by render that image? Okay, here's an image at the typical first-person shooter scenario, right? Image applied as a texture to the floor. Some resolution here, some resolution on the back, right? The same image, the same texture is on screen 65 pixels wide at the back, but it's 324 pixels wide at the front. So the sampling rate at the back is significantly lower than the sampling rate at the front, despite the fact that the texture is the same. Okay, so which one is my sampling rate? How should I subsample my texture? Do I want to subsample that so that it works in the back? Then it's probably pretty washed out in the front. Do I want to keep it at full resolution? Well, then it's probably going to alias on the back, or it's certainly going to alias on the back. So what we need to do is we need to subsample adaptively. We need to take the texture, and the same is true for meshes as well, but let's focus on textures here. Okay, so we need to take this texture and need to have the right version for the right place. Okay, and that during runtime. So if I'd be running down this floor to kill, I don't know, a friend, an alien, a zombie, whatever, that will change, right? For the exact same portion of the floor with the exact same texture, I suddenly need a higher resolution because I happen to run there because, I don't know, I want to kill the zombies there. Okay, so what can we do? Well, we would have to repeat, or we would have to adjust the texture or any of the data per frame. Yeah, so what can we do? Well, we can't do this during the rendering process. That would be too expensive, or we don't want to do this during the rendering process. That would be too expensive. Instead, what we do is, and that's a repetition again from rasterization before, I already explained this, to use the mipmaps. Okay, so we use those multiple resolution data structures that we have, that we call mipmap, multimap, palmom, map, that store the same data at multiple resolution. And then we just pick the appropriate resolution. So the problem is the appropriate resolution might be between two resolutions. Okay, so if we call them 0, 1, 2, 3, 4, our appropriate resolution might be 0.6. What we can do in that case is we take both and interpolate between the two. Okay, so it's again about interpolation. But the creation process is usually relatively straightforward. We take our original data and then we just subsample it and do this as a pre-process when we actually generate the game. Not when we run it, but when we like create the assets, draw them, and then store this data structure that will contain, that will require some more memory. But as I already explained a couple of lectures ago, it's not a huge deal, that additional memory. Okay, so you might want to go back to lectures about the details. But we store all those resolutions and pick the right one. And that's that's literally what MIP mapping is. Here's an interesting image. So what you can do is you actually have full control in rasterization pipelines over those MIP maps. So instead of just uploading one image at multiple resolution, you can, if you want to, upload completely different images. So you can set different images into those different MIP map levels. And what someone's done here is you uploaded an image that would be 1K in size, 1K times 1K, and would actually be red with the word 1 with a ton of 1024s in it. And for the next resolution, upload a turquoise version that has 512s in it, and so on and so forth. And it's really funny, if you use those textures in, for instance, a terrain rendering scenario, you can actually see how this MIP mapping works, right? You see your full resolution here, you see the interpolation between the different levels that's here in this area, and then you see the 512 version being used, and so on and so forth, right? And up to this point where in the very back you see those orange spots, that's the 16 by 16 version, and the smaller ones don't even fit on the screen. Okay, so this kind of MIP mapping at work. There's one curious thing that you might notice here, and that is, notice how, like, well, the resolution decreases, the text resolution decreases towards the back, which kind of makes sense, right? Towards the back, things get smaller, want to use a high resolution thing. But then, notice how suddenly we have different resolutions depending on the orientation of triangles, right? The top left, so there's this green patch in the blue mountain, right? Which is, green is 128 here. So, what does the texture resolution really depend on? I mean, I said, well, sure, it depends on the sampling rate. But again, that's easier said than done. How do we figure out for a point which resolution to use? Okay, and apparently it depends on things, not just the distance, but also the orientation, right? So long story short, and that'll be my last kind of argument in this lecture, and in the whole lecture for this whole semester, is like, how does this work? How do we figure out when we do a texture lookup? If you're interested about what a texture lookup is, you need to go back to my lecture on texturing. But how do we figure out not just the texture coordinates, those are probably given, but how do we figure out which textures to use? I mentioned that briefly during the texturing lecture, but here are some more details. So what we do is, we can, for instance, look at the neighboring pixels. Okay, so the neighboring pixels, assuming that they are in the same triangle, and there's ways how to enforce that, that they are in the same triangle, they look at the same texture. We can look at their texture coordinates and compute the distances in x and in y to the neighbors. So then what happens is, like on the top left, what you see is that's an object, two triangles, for instance, being textured with a checkerboard pattern. Now, if I take all my pixels that generate fragments, right? And those are those little orange crosses here. If I take all those samples and project them into texture space, so that's what you see on the right, okay? So on the right you see texture space, so now your checkerboard is nicely shaped, but the shape of this quadrilateral becomes awkward in texture space, right? So those are these, now the orange points, I've drawn them here as little green crosses. Okay, so those are the samples in texture space for the pixels. Now what I can do is, I can do for one of those, for one point that I'm interested in figuring out what MIP level should I use. Okay, I can figure out what's the extent of this awkward shape of this pixel in texture space. Okay, so how far is it away from the left sample, and how far is it away from the top? And what this gives me is a distance. Those are two distances. And to make things a little bit more complicated and theoretical, I could say those are partial derivatives. Okay, so distances between values are their, well, differences. The difference is a partial derivative, and this is an approximation of a partial derivative. So that's we call this a center difference or a forward difference, depending on what exactly we do. So basically this gives me, if I go in this direction here, it gives me the x and y differences. Okay, so how much do I, if I go into, say, u direction, okay, if I call this x is u here, how much do I differ in x and y? Okay, and if I go in v direction, how much do I differ in x and y? Okay, so and this gives me a total of 4 values, and those are the partial derivatives. Okay, those are 2 vectors, 4 values, 2 vectors. You can also think about them as 2 vectors, right? They're 2 x and y coordinate. Okay, so what I can simply do is I can look at those partial derivatives, or more simply, if you don't like calculus, you can simply say, look at the length of those 2 arrows. Okay, so I look at the length of those 2 arrows and I pick the longer one. That's where the maximum here comes. And from that length, I say, okay, the longer that thing is, well, that means the lower the resolution of the image has to be. And since if I just, for each resolution level, increase the size by 2 in x and in y, I can just simply take the logarithm of 2 of that distance d and I get my level. Okay, notice that that's a floating point. That's not an integer. Okay, this might be 4.8, which means I have to take the one at 4 and at 5 and compute the average of the 2. And just as a side note, how do you get the partial derivatives? That's simply the difference to the neighbors. If you do all of that, you get a level. On top of your texture coordinates, you know which level to look at. So it's actually a relatively straightforward process, right? It's just a difference between pixels. And if you want to consider this as calculus, which is perfectly fine, makes a lot of sense. But if that's beyond your math level, never mind the calculus here. Okay, so if I do this without mip mapping and with mip mapping, you see how things get smoother towards the back, because I now use, for those fragments on the back, I use a subsampled version of the checkerboard pattern here in this case, and it gets washed out instead of, well, crazy, really, right? I mean, instead of getting random yellow or red values, I get, well, the average between that yellow, red and white values. I get the average between this red and white here. Okay, so now literally the final remark about mip mapping is it's not perfect. It's not perfect. Why? It looks more washed out than it should actually be. Here's another example that nicely shows that. So that's obviously a runway, and that nicely shows, okay, well, towards the back, we don't have aliasing. It's not going to flicker, but it looks washed out. And notice how it looks kind of as if it's been stretched in X. And the reason for that is that if we were to compare those 2 partial derivatives, the difference in X and in Y, we would see that in Y we make this huge step, but in X we don't. Right? In X, of course, the sampling frequency decreases towards the back, but in X it decreases differently. And since we take the max over those 2 values, we actually we over smooth, or we reduce too much detail in X direction. Okay, if we would not do this, we would get this result here. Okay, so if we would actually reduce this appropriately in X and in Y differently, we would get this one, and that's what's called anisotropic filtering. Okay, so we would get this result that is, instead of computing the max out of these 2, actually taking these 2 partial derivatives, taking the distance X and Y, and using them separately, and having textures that are not uniformly subsampled, but that are just subsampled in X or just subsampled in Y, and we take the set of all those textures, which is big, that actually requires more memory, and we pick the right one with 2 levels. Okay, so the maximum is the issue here. And if we don't do it, that's what's called anisotropic filtering. And since it takes so much memory to store all those resolutions, excuse me, you generally don't want to store all those resolutions, but trick around. But that's probably something to talk about another day, because we're now done. So in summary, you can do a couple of things. You can do super sampling, you can do pre-filtering, and you can do post-filtering kind of along with that. So remember where I said the reconstruction is generally some sort of post-filtering, so we smear things out later on. Post-filtering is super popular these days, in particular with ray tracing approaches on GPUs. I mentioned a couple of times, so modern GPUs can do some ray tracing, but they're generally too slow to do this for every pixel, let alone super sampling. So they do this for very few pixels and then apply a filter to remove or to fill the gaps in between and remove any noise that were introduced in the process, right? Generally, you introduce some noise to get rid of regular structures, just like before, but there's a very sophisticated research on filters, on adaptive filters to post-filter things to get you to not notice the details, okay? To just have very, very few rays sample the scene and then fill the gaps in between by some sort of filter that might be very sophisticated based on artificial intelligence networks, based on machine learning. So they can be pretty complicated and almost impossible to understand because they're just the process of some machine learning process. Okay, so with that in total, you can now, if you take kind of the summary of all that I explained throughout this entire lecture, you know now a ton of different, or two actually, ray tracing, technically path tracing, rasterization, a bunch of different rendering approaches. You know how to represent data, how to represent meshes, how to represent textures, how to access textures. You should know all of that, or at least I explained all of that. So that's pretty much what it is. So what will be next? Well, next will be, if you want to, next semester. I hope not remotely. I hope that will be fully in presence. I guess we're hopefully have the situation, the pandemic situation, so much under control that we have present lecture throughout the entire next semester, and that will, and then I'll give the lecture on advanced image synthesis and kind of build on top of all of what I've explained this semester to, well, get either more effects, faster effects, or, well, new effects into all of these rendering techniques that I explained. So, with that, any questions? And in the meantime, I'll drink something. I have a question regarding the exam. Okay, sure. That's, I guess, inevitable towards the end of the semester. Can I read that? Is it like most oral exams that we prepare a topic to begin with and talk about it for 5 minutes and then you'll start? Yeah, sort of. Is it really with most? I thought that I'm kind of special here. Oh, my colleague stole my idea. No, that's actually exactly how I usually do it. So I'll usually ask you to start with something, and it's not fixed to 5 minutes. So I'm very flexible here. So some students take longer, sometimes it's quicker. So but generally I would say, okay, well, I'll just pick your topic from the lecture that you like most, and you don't have to do this. So that's probably difference, right? I mean, you said we have to. No, you don't have to. So there's a surprisingly large amount of students that say, no, I don't want to start with anything specific. You start. So that's fine with me. So if you want to start with something that you looked into particular, I'll let you talk about that. But I'll interrupt you if I have questions. So it's not like there's a fixed 5-minute slot that you have to follow, but there's some time in the beginning that you can, if you want to talk about something in particular. That's how it works. So in that case, the answer is probably yes and no to your question. So, anything else? Doesn't seem to be an immediate question. Again, Moodle is still around, so you can ask questions on Moodle. You can ask questions on email. As you've seen, it's quite a while until the exam. Oh, okay. And did I get it right that we can skip one question if we have the? Yeah, sure. That's what you got right. So if you get the bonus, I forget about how much it is exactly, but I'll get a list of students that in the exercises are beyond the, I don't know, what is it, 80, 50% or something. I can't remember, 80, I think it's 70 or 80. Anyways, you know when you get this, yeah, you have this kind of joker question. When are you going to talk about anisotropic filtering? Well, I don't think at all that much. The reason The reason I don't talk about anisotropic filtering in detail is because there's no anisotropic filtering as such. You could do anisotropic filtering very simple. Just instead of having, say you start with a 4x4 texture, to keep things simple. You start with a 4x4 texture and you compute your mid-map, 2x2, 1x1. Okay, instead of just creating those two, you can create again, we start by 4x4. You create a 2x4, 1x4, 4x2, 1x2, 2x1, and 1x2. Okay, then I think I got them all. Okay, so you basically create all subsample versions that are combinations of 4s and 2s and 1s. You store those, and then when you do your partial derivative computation, you get those two values, and then you pick the one subsample version that fits. Okay, so that's perfectly fine. Nothing wrong with that, except it consumes a lot of memory, in particular for large textures. So what vendors do is they cheat. They cheat in one way or another. And I can't talk about those details because they're, again, trade secret. They're different. They're not even documented. There's ways how to figure things out. But, and they change. Okay, so with every generation of graphics cards, and even driver releases, the vendors change the implementation. So if they have more memory, they can move more, they can cheat less. Okay, so but the bottom line is the actual anisotropic filtering approaches are somewhere between this approach that I just described, like compute all of the levels, and the other extreme is only have the mid-map and compute those partially subsampled versions on the fly. Okay, so do exactly what I said you don't want to do, is compute this on the fly. But of course, again, you have compute time to spare when you're short on memory. So somewhere in between those two situations, have all versions and have only the mid-map and compute this on the fly. That's where your implementation is with your specific driver and your specific piece of hardware, and it differs. Okay, so like there simply is not the anisotropic filtering. Okay, so anything else? Okay. Good. Again, as I said before, there's still Moodle, there's email, there's technically the telephone around. When the exact names will be published, I think the poll is still open. I guess I left it open until the end of the lecture time, which is this week. And there's still very few entries. I think we have about 30 registered students and 10 or 15 have registered so far, which is kind of normal. You know, in particular, ISE students, they can register for they tend to register for pretty much any exam and then just don't show up or cancel shortly because there's no penalty for not showing up. At least there was no. So long story short, it's kind of normal, but that makes it very hard for me to predict when we're done. So the only prediction that I have is when I close the poll, and the poll closes, I think, end of the week, and after that I'll go through this. So we'll probably publish sometime the next week. Okay. Okay. Anything else? Okay, good. Then that's it. That's it for the semester. Yeah, you seem to be the only one asking question here. Okay, so yeah, that's it for the semester. See you in the art exam. That will be the point where I'll start to ask the questions. So we'll kind of swap things around. See you. Until then, stay healthy and bye-bye.